Okay, in this video I want to talk about uncertainties again and go into a bit more detail about these. The first thing I want to talk about is some things that we can do to reduce the effect of uncertainties and to make things more accurate. So let's start off with this. Right, so if you look at this sheet that you've got in front of you here, some of the things we can do to reduce uncertainties are repeat all measurements and calculate mean values. As we said in the previous video, this reduces the effect of random uncertainties and is likely to make our result more accurate. The other thing that we need to do is to collect at least 5 values of your independent variables. So if you were doing an experiment taking data for a pendulum of various lengths here, this is our independent variable, so we take 1, 2, 3, 4, 5 different values of that and record the time period for each of those values. If you used 4 values, for example, that would be basically inadequate data. It wouldn't be adequate because there would not be enough values of the independent variable investigated. And that means that when you plot a graph, you can't really spot the trend or pattern in your results. So you need to take at least 5 values of the independent variable and record results for that. Another example here is if you're dropping a ball, for example, to measure the bounce height of that ball. When the ball bounces up, it moves very quickly. It's difficult to measure its bounce height against a ruler. So what you can do there is just film it with an iPad and play it back in slow motion, and that will give you a more accurate reading of the bounce height. You want to calculate results over as large a range as possible. So in this example here, we've got a 1 meter length pendulum. You want to record results over the full meter length. So you wouldn't want to just take results for 0.8, 0.85, 0.9, 0.95 and 1 meters, for example, because that would just be a small section of the full length that you've got. You want to take the full range. So you can see here we're starting with 0.2 meters and working up to 1 meter and covering a large range of the length of our pendulum. Okay. Again, you can see that the difference between each of these values here of my independent variable is 0.2 meters. So I'm going up in equal steps, and that's good practice. If I was going to measure, let's say I wanted to measure the thickness of a piece of paper like this, you can't really measure that with a ruler. It's too small. It's less than the resolution of my ruler. So there's a couple of things you can do here. You could take 100 sheets of paper and measure the thickness of that with a ruler, and then divide your value by 100 to get the thickness of one piece of paper. The same for microscope slides. Measure 10 of them, divide by 10 to get the mean thickness. This makes your result much more accurate. Another thing you can do is use a pointer. If you're going to measure the extension of a spring, set it up with a pointer that points towards your ruler next to the spring. That will make your reading of extension potentially more accurate. And then finally, we're talking here about parallax error. If I want to record the volume of water in a measuring cylinder, I need to get down to eye level to measure where the meniscus lines up with the reading on the scale. Or if again I'm measuring the extension of a spring, I need to get down to eye level. Otherwise, the spring or the mass that's on the spring might project onto the ruler at an angle and give you an incorrect reading, which is known as parallax error. Okay, so if you're here, sorry about the terrible drawing here, but if you're here and you're measuring the extension of this spring, so here's your spring here, okay, and there's your ruler there. If you're looking from here, okay, then you're going to see that, hang on, looking for the mouth there. You're going to see that this projects onto the ruler down here, and you might read the extension as that reading there. That's called parallax error. You need to get down to eye level so that you can measure it like this, and then you get the correct reading, okay? So that's parallax error. So we want to try and do all these things to make our results more accurate, okay? So that's the first thing in this little video. Now, the next thing I want to talk about is just very quickly, let's go for another sheet of paper here. We want to talk about the resolution again of a few more instruments, okay? So, analog Vernier caliper. So you know that we sometimes use a Vernier caliper to make measurements. This is a more this is a measuring instrument that has a higher resolution than a meter ruler. So a meter ruler, as we know, plus or minus 0.1 centimetre or plus or minus 0.001 metres or plus or minus 1 millimetre. An analog vernier caliper is plus or minus 0.1 millimetres. That's its resolution. That's the smallest reading it can take. So it's going to give you a more accurate result probably. A digital vernier caliper is able to read to an even higher resolution. This can read to plus or minus 0.01 millimeters. Okay, so this is able to read really small thicknesses. You could try and measure the thickness of a piece of paper with that. Also, a micrometer has the same resolution, plus or minus 0.01 millimeters. So in an exam or in past exam questions, and when you look at the mark scheme, you may see a micrometer referred to, or a digital vernier caliper. These are the devices that measure to 0.01 millimeters. Now, when I was in school, I used a micrometer, but they're quite difficult to read the scale of, particularly when you don't use them very often. So we use a digital vernier caliper in school. They're much, much easier to read, and the WJEC are perfectly happy with you using those. So if you're asked to talk about what you would use to measure the thickness of a piece of wire, for example, the diameter of a piece of wire, you would use a digital vernier caliper. In the mark scheme, you may see them saying use a micrometer, but it's perfectly fine to say digital vernier caliper because they have the same resolution. Okay, so that's the next bit. All right, so let's move on then from that and talk about uncertainties and how we calculate them. So I think at that point we'll stop there, and then I'll do another video on calculating uncertainties.